In this class, we will talk about velocity fields. When we talk about velocity fields, we're really talking about, consider again the case of our airplane. We got the airplane, and I want you to think about a small fluid particle that's moving. I want to understand the behavior of that particle. I want to understand how does it move across and around my airplane. Um, so it's not only applicable to airplanes, it's applicable to many different examples. As for an example, think about this, think about the car, right? A simple car, this is actually what your velocity fields will actually look like in your car. And I want you to think about a small particle right here at time sub-zero, okay? That particle now is moving. If the same particle has gone somewhere here at time 1, the same particle has moved somewhere here at time 2. So, and I want to know at what speed it's moving, right? I want to know from here it moved at speed sub-zero. It has an initial speed. What is the speed here and what is the speed there? I want to know the speed at which each one of each particle is moving across my domain. So this becomes a very important topic of conversation. To understand how this works, let's consider there are two different cases. There's the case of steady flow and there's the case of unsteady flow. For the case of steady flow, well, before we do that, let's do this. Let's consider these cases. Let's consider three different cases. So we have the case of steady flow. It's a flow where velocity and everything will remain completely constant. Everything remains constant. The temperature, the velocity, everything. The case of quasi-steady is, well, you can have some variation. It's not large. It's very small variation of velocity, but everything else is kind of at the end of the day cancels out, remains constant. So the sum of this will actually equal to 0. About this, not 0, about the mean, give it the same mean value. Unsteady flow is one that's actually drastically changing with time, and we know what that value actually looks like. So if we did this, we can go ahead and we can start with our coordinate system. Think about the coordinate system X, Cartesian coordinate system, X, Y, and Z. We could have this as well, polar coordinate system, cylindrical coordinate system, any coordinate system that we want to. And let's suppose we have a particle there and we want to know the speed. We want to know the speed, we want to know the pressure, the temperature, etc., in that particular point. Okay? So given that, and we want to analyze this, we got two cases. Mainly two cases are the ones that we're going to study here. One is steady flow. The other one is unsteady flow. Okay. Then these steady flows are time independent. The quantities don't depend on time. Here the quantities are time dependent. Okay. Then we could have, let's say, velocity. Okay, we had velocity is a function of x, y, and z. That's the coordinate where that belongs to. But here, unsteady, yes, it belongs to x, y, z, but it's also a function of the time when that event occurs. Maybe you have the case of a pressure. Okay, so if you have the case of the pressure, it can also be a function of x, y, and z. And it's a function of x, y, and z, function of time. Think about temperature. t is a function of x, y, and z. And this the temperature is x, y, z, and also a function of time. So in other words, I could have any other quantity I wanted, I was interested in, and basically whatever that quantity is, let's call the letter x, and it's a function of x, y, and z. So function of x, here's a function of x, y, z, and time t. Okay? So so we are interested mainly in steady flow, but beyond the course, you can take a higher level course we talk about that will teach you more on steady flows. So let's consider, so anytime a flow that's starting, okay, at time equal to 0, and the flow is starting, this is your start point, that flow that's going to start, that flow is going to also always be unsteady. Okay, it's an unsteady flow. It has to start at 0 velocity and has to evolve itself into what we call eventually, after some time t1, has to become completely steady. Okay. Let's suppose at time t2, I am going to start to, at time equal to t2, I am going to start my process to stop. I'm going to stop now at time t3, but this process from here to the stopping point will be an unsteady event as well. Okay, if I can just plot this for the sake of this discussion, if I could do this, this is time, and let's say speed, velocity. So you're starting at a 0 velocity, you're going to go somewhere there, and then basically stays there and come here. Now it's going to go down here. So you can see that any event that's between these 2 points, I can safely say that they are basically constant. Okay, the events are constant. If it's a steady state flight, there's no extra conditions, additional conditions that will make it unsteady. Okay, so now consider, to further understand this concept, consider this. You got x, you got y, you got z, and you got the streams. You got the streams that are going there with your flow. Now let's consider you have a small particle here, okay? At point 1, the particle now has moved to point 2, okay? So the particle moved, okay? So let's assume that at point 1, the coordinate systems x, y, and z. At point 2, my new coordinate system, if you would agree with me, is x plus dx, y plus dy, z plus dz. Okay, so your vector, sometimes I'm going to use the notation vector like this. Sometimes I'm going to write the underscore underneath the variable. That's the vector for me. It's the same thing. So it's I plus y plus z times k. And then dr will be dx y plus dy plus dz k. Okay. So let's see what is happening here. Before we do that, let's just kind of pause for a moment and let's see some of vector calculus, review a little bit of vector calculus here. If I had f was a function of x, y, and z, then d of f would be nothing else than partial of f respect to x, d of x, plus partial of f respect to y d of y plus partial of f respect to z d of z. This is using Taylor series expansion and keeping the high order terms out. Now realize from here the following, that this term, this term, these terms are included in my vector dr. D of x I plus dy j dz k. You can see these values are, these are the same quantities are included there. Now, another property that you can remember, what is the gradient of f? Okay, so the gradient vector is nothing else than partial of x I plus partial of y j plus partial of z k. So then the partial of f will be partial of f I plus partial of f y plus partial of z f partial of z k. And so if you realize now, if I take a dot product between these two numbers, this is a vector, by the way, there's an underscore. This is what I will get. So if I take the dot product, okay, just as a reminder, what's a dot product? If I had a vector A, A1, B1, C1, I had the vector B, A2, B2, C2, then A dot B is equal to A1 times A2 plus B1 times B2 plus C1, C2. I get a scalar. Okay, it's not a vector anymore. So that's the same concept we will use here. So if I want to find dr, I want to find what df is. Df would be nothing else than taking the gradient of f, dot product dr, and you can show that indeed you get the same equation that I started with. And this expression is very convenient that we use it, because that means I can use it in a more general way for any coordinate system possible, and is very helpful. Okay? So this is the linear vector calculus that we'll be using later on in the class. The next thing I want to introduce to you is how we write the vector, vector field. Velocity field. Okay, how do we actually write the velocity field? What is the mathematical expression for the velocity field? Okay, so the velocity field, again, this is for the Cartesian coordinate. Let's call this is x, this is y, this is z. I have a point right here, and that's the point in which I want to calculate all these values. So b, again, just a reminder, this is the same as a vector. Okay, this is a vector, and it's a function of x, y, z, and can be a function of time in the most general form. Okay, so if I'm going to expand this, this is the same as v of x, function of x, y, z, and t of I, plus vy x, y, z time j plus vz x, y, z, t times k. Conveniently, we typically express this, we call this letter u, we call this speed constant letter v, we call this speed constant, oh, not variable, W. Okay. So as an example, think about, let me give you two examples. If it's a steady flow, your expression can look something like this. V is a function of x, y, and z, will be x squared I plus xy j plus 3 times k. If it's unsteady flow, then v is going to be a function of x, y, z, and t. But now note that I can have this constants. I can be multiplied by a t in the problem as well. Okay. Another variation to these problems for unsteady flow is the following. Okay. For unsteady flow, we can also have the following. We can say, you know, the velocity at a given point, let's call it P, is going to be a function of time, fully a function of time. What I mean is that this is going to come from the following. This is going to come from the following. It's going to come from a position vector that's a function of x, that's a function of time, I, plus y, that's a function of time, j, plus z, that's a function of time at k. Now you can see that this is not anymore a function of x, y, z, because these are, my x is a function of time, y is a function of time, and z is a function of time. So if I wanted to go from my velocity to if I wanted to find my position vector, I can simply integrate this respect to time, and that would produce the position vector. Okay. If I did the opposite, I went from a position vector, I can take the time derivative of rp, and that would give me my vector, that would give me my velocity field vector. I can also find my acceleration. The acceleration at p would be nothing else than the derivative of t of vp. Okay, so if you wanted to see how this really works, your velocity vector, okay, this quantity right here will look like this. Okay, velocity vector would be nothing else than dx dt I plus dy dt j plus dz dt k. Because this is really a function, this is strictly a function of, this whole thing is a function of my time. Okay. And then realize that this is nothing else than v of x, this is v of y, and this is v of z, as we had before. The only difference is now this is all a function, only a function of time. In this way, I can say that v of x is a function of time, a function of x, y, and z, but since x is a function of time and y is a function of time and z is a function of time, then all these are functions of time, and all I have is an expression in a function of time. So let me just, for an example, let's suppose this was t squared, this was et minus t, this was 1. So if you look at your velocity vector, your velocity vector will look something like this. Your velocity vector may look something like this. X squared plus y, I, y, j plus 1 z, 1 times z k, right? So here particularly what's going to happen is, now this is a function of time really. So what you can do is, if I want to take this, I can replace that here. Now this becomes nothing else than t to the 4th. You can see replacing this here, plus e to the minus t, I, plus e to the minus t, j, plus 1 times k. You can see that everything now is only a function of time. So in these problems, this is what we have. To better understand this, consider a very simple example. If a simple example would be the velocity vector is xi minus ji, okay? So what I can do is I can say, you know what? I know that d of x dy is equal to vx, and that is actually the y, x, and I know that dy of t is equal to minus y, okay? So if I just dealt with this equation first, and I went on both sides, and I said this is going to equal to dt over x, okay? So I just took this equation, dt dx. I can interchange, cross multiply. That would give me over x. That would give me dt. And here I can integrate from time 0 to t. Here's the initial position, 0 at time 0. And this is my actual function of x of t that I'm looking for. So if I was to do that, this gives me, this integral gives me natural log of x, and it's evaluated x sub 0 and at the function xt, and has to equal to t. Okay, and then if I keep moving on, you realize that this gives you natural log of x minus natural log of x sub 0. This is a constant, will equal to e, or using some of the properties that we know, this is x over x sub 0 equal to t, and I can take now on both sides, I can take the exponential value, right? And then this side gives you nothing else than x over x sub 0 is equal to e to the tth power, and that will produce the following answer. X of t is equal to x sub 0 e to the t. That it will be your function x that was actually used to find that velocity. If I wanted to find y, you can show similarly that y is the same process. It's going to equal to y sub 0 e to the minus t, and that minus t actually comes from the fact that there was a minus involved there. And you can also show that in the problem, since your vz was actually equal to 0, then your integration will give you z of t is going to give you c sub 0 is a constant value. Okay, So this is some ways how we can handle the flow field, your your speed velocity field, your speed field, and you have to watch out if you're working in if you're working steady flow or unsteady. Most of the problems we will do here is for steady, so we will stick with the steady flows.